Have you ever wondered why some electronic circuits perform flawlessly at lower speeds but start to struggle or distort when things get really fast? It is a critical question for engineers, and understanding these limits is fundamental to robust design. Measuring the frequency response of an inverting amplifier involves applying a sinusoidal input signal and systematically varying its frequency while maintaining a constant input amplitude. As you sweep through the frequency spectrum, you will record the amplitude of the output signal and its phase relationship to the input, allowing you to characterize how the amplifier performs across its operating range. The why behind this measurement method lies in the intrinsic characteristics of operational amplifiers and their feedback networks. Operational amplifiers are not ideal components. They have internal capacitances and finite gain bandwidth products. As the input frequency increases, these internal capacitances begin to shunt the signal, reducing the open-loop gain. The negative feedback in an inverting amplifier then works to maintain the desired closed-loop gain, but as the open-loop gain drops, the closed-loop gain will eventually start to decrease as well, typically at a rate of 20 decibels per decade. To practically perform this measurement, you will use a function generator to create the sinusoidal input and an oscilloscope to observe both the input and output signals. Start by setting a low input frequency, perhaps 100 Hz, and measure the peak-to-peak voltage of both the input and output. Then gradually increase the input frequency, taking new measurements at logarithmically spaced intervals, such as 100 Hz, 1 kHz, 10 kHz, and so on, extending well beyond the amplifier's expected bandwidth. Simultaneously, you will note the phase difference between the input and output waveforms, observing how the output lags further behind the input as the frequency rises. An insightful detail here is the concept of the gain bandwidth product, often referred to as GBP. This product, specified for an operational amplifier, indicates that, as you increase the amplifier's gain, its usable bandwidth decreases proportionally. For example, an operational amplifier with a 10 MHz GBP will have a bandwidth of 1 MHz when configured for a closed-loop gain of 10. This inverse relationship is a cornerstone of operational amplifier design and explains why frequency response measurement is not just about observing performance, but also about validating design choices against these fundamental limits. By systematically collecting this data and plotting the amplitude ratio, often in decibels, and the phase shift against frequency, you gain a clear picture of the inverting amplifier's limitations and capabilities. This methodical approach allows you to identify the 3 decibel cutoff frequency, where the gain drops to 70.7% of its maximum, and understand the amplifier's stability margins, ensuring your circuit will operate reliably within its intended frequency range without unexpected oscillations or signal degradation.